Welcome to this explainer. Today, we're tearing into the ESP32 microcontroller. I mean, think about it. A dual-core processor, integrated Wi-Fi, Bluetooth, and enough GPIO pins to literally run your entire smart home, all packed into one stunning piece of modern engineering.
Okay, let's dive into this. How do we take this intimidating, almost abstract powerhouse of Internet of Things tech and bring it all the way down to an approachable physical reality right on our workbench? Well, that is exactly what we're going to master today. But first, to really grasp why this tiny little chip matters so much, just think about this number, 8.4 billion. That is the estimated number of connected devices out there right now. To put that into perspective, there are only about 3.2 billion human internet users, so devices far outnumber us. And the ESP32, it's literally one of the main engines driving this incredible IoT revolution, quietly running everything from our smart homes to industrial sensors.
The original ESP32 hit the scene back in 2016. But, tech evolves fast. To meet different demands, Espressif Systems completely expanded the lineup. They rolled out single-core models like the S2, and then by 2020, they even shifted to a RISC-V architecture with the C3. They basically custom-tailored these chips to handle entirely different power and memory constraints. It's like a whole family tree of microcontrollers. Now, what's really interesting about this slide is the sheer processing power they managed to pack into this tiny module. We're talking about the Extensa dual-core 32-bit LX6, the absolute brain of the original ESP32. It screams along at up to 240 megahertz, packs 520 kilobytes of SRAM, and has Wi-Fi and Bluetooth baked directly onto the die. It's essentially an entire computer scaled down to the size of a postage stamp. Crazy, right? All right, but enough of the slick high-tech theory. When you actually go out to buy one of these for a project, you've got a choice. You could buy it the bare microchip, but honestly, that requires some seriously advanced custom circuit board skills. Or you can do what most of us do, grab a pre-built module. It pieces the whole shebang together and breaks out those microscopic connections into actual header pins we can plug straight into a scuffed-up prototyping board. Way easier.
So the crucial point is this magic number right here, 3.3. If you're coming over from the older world of 5 volts Arduino boards, you absolutely must hardwire this rule into your brain. The ESP32 relies strictly on 3.3 volt logic. Seriously, if you feed 5 volts into most of these pins, you are going to fry your board immediately. Not a fun way to end an afternoon.
These dev boards have some really highly specialized pins, and this brilliantly illustrates that we're not just dealing with basic power and ground here. For instance, notice that GPIOs 34 through 39 are input only. We've also got 18 analog to digital converter channels. But get this, 10 of these pins are actually capacitive touch sensors. They detect tiny variations in electrical charge, kind of like human skin. Meaning, you can trigger your code literally just by tapping a raw wire with your finger. How cool is that? Okay, but before you start aggressively plugging jumper wires into everything, heed this warning. Never, ever use GPIO pins 6 through 11 for your custom circuits. On the ESP32 module, these specific pins are internally tied directly to the board's integrated flash memory. So if you try to use them to, say, read a sensor or light up a display, you'll disrupt the chip's ability to read its own memory, and the whole thing will just crash. All right, let's actually get our hands dirty and build something, a simple blink circuit on a messy breadboard. The physical wiring takes just 3 quick steps. First, we place a standard red LED across 2 different rows on the board. Second, we connect a 220 ohm resistor going from GPIO 5 over to the LED's long leg. And finally, we just run a standard jumper wire from the LED's short leg straight into a ground pin on our ESP32. Boom, hardware sorted. Now you might be wondering, hey, why don't we just plug the LED directly into the pin? Well, that 220 ohm resistor is absolutely necessary. It's a passive component that acts like a bottleneck for the electricity. Without it, that 3.3 volt pin would push way too much current through the LED, and it would literally burn out with a tiny little pop before you ever even got to see it blink. Let's move to and see how this builds over on the software side. If we look at the code on our screen, every ESP32 program basically has 2 main parts. First up is the setup function. This runs exactly once the moment the board gets power. By calling pin mode, we're explicitly configuring GPIO 5 to send voltage out into the physical world rather than, listening for a signal coming in. Next, we have the loop function, and this bad boy cycles endlessly. It tells GPIO 5 to write high, which pushes out 3.3 volts and turns our LED on. Then it hits a 1-second delay. Right after that, it writes low,
dropping the voltage down to 0 so the LED turns off, and then it waits another second. It just repeats this exact pattern infinitely. Upload that code, and you've just executed the hello world of microcontroller programming. Just imagine those digital pulses traveling out of the chip, flowing through those physical jumper wires, and bringing that red LED to life. You've officially bridged the gap. Software code has become physical hardware action. But hey, a blinking light is literally just the beginning. The ESP32 is a seriously advanced IoT tool, and power management is where it truly outshines the competition. You don't have to leave the whole chip running at full blast all the time. You've got 5 entirely different power modes, ranging from active all the way down to hibernation. This means you can selectively turn off the Wi-Fi, the Bluetooth, or even the main dual-core processor itself to save precious battery life.
And that brings us to the absolutely incredible efficiency of deep sleep mode. When you use the ultra-low power coprocessor to just quietly monitor a sensor, the ESP32 draws a mere 100 microamps. That's almost nothing. It can sit out in a forest or tucked away inside a smart home gadget, just barely sipping power from a tiny battery for months or even years, waking up only when it actually needs to transmit data.
So, we have traveled from a high-level digital blueprint all the way down to a scuffed-up, real-world, functional build. You've seen the specs, you've learned the critical 3.3-volt rules, and you've watched the code turn into physical action. The capabilities packed into this tiny little module are just staggering. So I'm going to leave you with this one question to think about. What real-world problem is your first ESP32 build going to solve?